So, welcome to the Allora Research Fireside Chats, where we're exploring the key ideas shaping decentralized machine intelligence and AI. So, in this episode, we're going to discuss how to synthesize decentralized swarm intelligence, so why it's needed, the challenges involved, and how Allora's approach creates emergent intelligence that outperforms individual models. So, I'm joined by Diedrich, our head of research, who's been leading the design of Allora's decentralized intelligence framework. So, hey, Diedrich,
Hey,
great
Steve.
to be
Great.
chatting. So, I think let's
Yeah,
start at the very beginning. Why do we need decentralized intelligence in the first place?
that's a great question. I think there are actually many different reasons for it along several different dimensions. I think there are probably ideological reasons, there are technical reasons, and there are probably also economic reasons. So on the one hand, what you see at the moment, right, is that artificial intelligence or machine intelligence is very siloed. And I think there is a good historical reason for that. The historical reason is that in order to achieve high forms of intelligence, you need computational power, you need access to large volumes of training data, and you need to have the algorithms that actually pull it off in a meaningful way. And it turns out that achieving all of these requirements simultaneously is quite hard to do.
Yes,
And
outreach for most people.
yeah, indeed. So for that reason, you end up in this situation where basically only a few players have been capable of gathering the resources to do that. As a result, it is also highly proprietary. And you end up in this situation where it is where the machine intelligence is siloed, where it is not very transparent, where it is potentially monopolized. And of course, we're starting to see deviations from that. There exists some like open source simpler models. Now, of course, with DeepSeek, you have an open source LLM that is actually publicly available. So these things change slowly, but even then, you're still like using this single model. So yeah, I think there was an obvious sort of ideological or policy related reason why you would want to have decentralized intelligence. It introduces a way in which machine intelligence can belong to everybody participating in that decentralized system.
Absolutely. So by being decentralized, it means that anyone anywhere can plug in, use, join, and get benefits from the network.
Yeah, exactly. And that is, I think, just yeah, also philosophically is important. Also, if you think about potentially the dangers of AI, if you think about smoothly integrating AI into society, alignment, and so on, then you kind of want to have this sort of common responsibility across the network and transparency.
Yeah.
So that is, I'd say, on the more ideological or philosophical side, why it makes sense. But then there is also a technical reason, and I'll get to economic at the end. But technically, what you see in AI algorithms is that they are the most accurate and the most successful if you're capable of maximizing the connections between different nodes within a network configuration. Basically, AI relies on the free flow of information, association, and inference. And if you silo these different models, then what happens is they don't actually have access to each other's expertise.
Yeah.
So
It's like it's a network effect. Is it
exactly.
similar? Is that a
Yeah.
way to think about it? Yeah.
Yeah. And if you have that network effect, then your AI algorithms can end up being a lot more efficient, accurate, and so on. So I think that is actually the fundamental technological reason why decentralized AI, and I suspect we'll get to that later in the conversation, but decentralized AI will always outperform the individual participants within a network. And that is like, it's almost like a standard inequality.
Yeah. It's a no-brainer in colloquial terms.
Indeed. Yeah. And for that reason, you technically want to try and coordinate multiple models or swarm of a very large number of models to collaborate one way or another. and together be greater than the sum of its parts.
Yeah. Well, that's. I mean, conceptually, I think it's a very clear idea. But so I all on board with that. But why don't we just plug infinitely everything into each other and solve everything? So there must be some
Yeah,
technical challenges in actually trying to decentralize this and bring these models together.
that's a good point, indeed. I think actually the biggest hurdle is both data and model privacy. So often the training data contains some form of private data that model
Right.
builders don't want to share. Of
Yeah.
course, model builders don't want to share their model either. So you need to come up with a situation where you can ensure data and model privacy, but still somehow share or combine inferences in a way where yeah, there is a positive resonance and these combine to a better inference.
Yeah.
So that is the other sort of technical aspect. Of course, there are technical limitations of like running models in a combined way on chain, for instance, or so. That is
Yeah. So like
technologically
computational limits. So there's only so much that you can process on chain. Yeah.
exactly. So for that reason, there were multiple reasons why this sort of idea of hey, maybe we can combine inferences somehow. That is preferable. So yeah, it's I think both privacy and computational limitations are touching on that. Um, but yeah, I think there was also a third way or a reason why decentralized intelligence is desirable, and that is economic. Because if you silo your machine intelligence, then you end up in a situation where the monopoly situation is basically allowing the bigger players to just dictate what the cost is.
Yeah.
And if instead you create an intelligence market effectively, you commoditize machine intelligence, you end up with a market that is considerably more efficient and therefore drives down the cost of machine intelligence while at the same time improving its accuracy and performance. So economically, what you do is you're not just in terms of transparency and accessibility and so on, democratizing machine intelligence, but also from an economic standpoint, you're democratizing machine intelligence because you make it economically accessible as well and affordable.
Yeah, that's true. But how do you? I mean, there must be some kind of different people in the network have different incentives, and they're sure everyone's trying to improve the model accuracy, but people want to get some reward for participating in the network. Is that a challenge?
Yes, so that requires some careful thought. Um, but there are ways in which you can do that, right? What you have to do is you have to think about what the role is of each individual within the network, and then try and match the incentives to that role. I don't think there exists a solution where the incentive structure is the same for all participants in a network, regardless of their role. You need bespoke incentives for different roles within the network, which leads immediately, I suppose, to the next question is why would you even need different roles?
Absolutely. Yeah. That's
Um, but the truth is you do need different roles because if you let's say you have a network of models
yeah.
and those models all provide their inferences, then who's going to decide which models to listen to?
Well, listen to mine. Mine's best.
Exactly. Oh, no, but that's the point. Like if models need to decide of one another,
Yeah, it's
who
incentive
is
misalignment.
winning the game?
101. Yeah.
Indeed, if they decide who's winning the game, but they're themselves participating in the game,
Yeah.
then you introduce a clear form of incentive misalignment.
Yeah.
And there are ways to solve this. Like there was probably the most famous attempt at that is what BitTensor have done. But even then, you're very susceptible to this concept that there is collusion between models or groups of models, or maybe even all models
Yeah.
within this network. And then, yeah, they can basically take over what is happening. So you can solve that by introducing sort of a different class of participants who referee what is going on and make sure that their incentives align with speaking the truth, which is different than the incentive of somebody providing a model who would should be incentivized to produce the best possible model, right?
Yeah.
That's a different incentive than speaking the truth. And by differentiating these things, you can basically start addressing these different aspects.
It's like I'm how that's the broad concept. So how does Allora do this in practice? Like, what are the different rules? So you've covered, I guess, in general terms, but how does this come together in practice?
So, in a lot of different ways. So, are you asking specifically about incentive structures, or
I
are
think
you talking
we've
about?
touched on, yeah, we've touched on lots of things. We've touched about the general problem and
Yeah,
the potential problems with it. I think I'm and the way that different people can act on the network. I think it's so how does is Allora ensuring that it does all this and at the same time the network has a superior collective performance?
right, right. So what that means is you need to find a way in which you can best combine all the individual inferences, right? Or potentially choose which one is best, or either way come up with a way in which the network provides one sort of best answer.
Yeah,
And the way in which this is done within Allora, we call inference synthesis. And basically, historically, what you see is that in these types of federated learning problems, where you have to combine the inferences of many different models, what you see is that the models sort of generate or accumulate a form of historical reputation. And that historical reputation then ends up setting the weights of these models. And then, like, the joint inference is a form of weighted average between all of these different input inferences. The the fundamental problem with that, if you want to do that, is that it is basically blind to the context within which the problem currently exists. So let me give you an example.
yeah. An example would be good here.
Yeah, so let's say we have two different. We have a network of just two models,
Yeah,
and one of the models is much better than the other model. So model one is awesome. Model two is pretty bad, except on Mondays. For one reason or another, I don't even care what it's
yeah.
predicting.
Yeah,
On Mondays, model two is much better than model one.
right.
And that is probably because of some context. It's a differently designed model that, just for one reason or another, on Mondays, the problem set is such that it outperforms. Now, if you use these sort of this historical cumulative reputation, you end up in the situation that the network will always weigh model one better or more
Yeah,
heavily than model two, even on Monday. That means that the network on Monday will do badly,
yeah,
because model one does badly, model two does well on
yeah.
Monday.
It's not aware of changing performance.
Exactly.
Yeah,
And this is indeed is what we initially called at Allora. We initially called the Cassandra problem. Is because of the priestess in the legend of Troy, who had foreseen that the Greeks would come and would invade the city with a wooden horse, and
yeah.
nobody believed her.
Understood.
That was due to some curse from the gods, but the point was fundamentally is that nobody believed her, and she was on her own.
Yeah,
And the point is that if you want your machine intelligence network to exhibit a form of this sort of context awareness of which model is right when, you want it to recognize and listen to the Cassandras.
yeah,
Because if Troy had listened to Cassandra, then the city would not have fallen. So that in this analogy is what you would want to do in the network. You would want the network to know, oh wait, it's a Monday. I should be listening to model two today instead of model one. And of course, there's an extremely simplified example where there's just sort of one dimension, which is which day of the week is it, that determines who is doing well. But in practice, you have a very complex situation and data space wherein some models will do well in sort of certain parts of that data space in certain contexts.
yeah,
And that is not something that, let's say, an on-chain or decentralized machine intelligence network can easily learn. This is the type of problem where you need machine intelligence itself
yeah,
to recognize who is doing well under which
Yeah.
circumstances.
So the machines are able to look and see the past performance of all the different people that making inferences and predictions and work out the patterns to say in these certain circumstances, then this model does really, really well, and these other ones don't do so well. So they would then
Yeah,
weight in that instance that model better, and thereby improve the overall network.
exactly. So the way we've done this in Allora is we've basically introduced. So we have the inference workers, which are basically models who just provide inferences,
Okay, so
and
it's
then we
making
have. Sorry.
just making predictions.
Yes, that's right.
Yeah, yeah,
So then we have this second type of participant in the network, which we call the forecaster. And the role of the forecaster is basically it basically is somebody who provides the output of a different type of model.
yeah,
This type of machine learning model or machine intelligence model is predicting what the performance of the inference workers is going to be. So how well they're doing basically is predicting their loss
right.
at the current time for the current task that they're about to submit. So it basically it can use the entire current context, that machine learning model, and say, well, turns out I've spotted over the last couple of weeks that model 2 is really great on a Monday.
It's a Monday, and today's a
It's
Monday, right? Yeah,
exactly.
yeah, yeah.
So therefore, I'm just going to predict that model 2 is going to have a very low loss. That means high accuracy, high performance. And model 1 is going to have a high loss, so a low accuracy, low
Right.
performance.
And
And then what the
presumably, if there was, yeah, and if there was someone else on the network who was performing this forecast role hadn't spotted that, so they would get rewarded for spotting. Haha, Mondays are key here, and
That's right.
yeah,
So what the network then does is it says, okay, let me collect these forecasts. And based on these forecasts, I'm now going to assign weights to these models, to these inferences.
yeah,
And I will construct what is called a forecast implied inference for each forecaster. And what that is really is a weighted average of all of the raw inferences coming from the inference workers, but just by setting the weights according to the forecasted losses coming out of each of the forecasters. And then each of those forecast implied inferences is just added to the inference pool together with all the other inferences. And then these, all of them, achieve their historical reputation, based on which then Allora, the entire network, sets weights and combines all of these together.
yeah,
And what you see in practice is that these forecast implied inferences, of course, do better than raw inferences because
yeah,
they have this ability to pick and choose depending on what the context is.
yeah,
So that is why then these in the end get higher weights, and why the network at large, the entire sort of network inference that you end up with in the end, is outperforming any of the participants too. It is basically relying on that role, on that context-based information to say like, okay, of course the forecast implied inferences are better than the raw inferences. So therefore we weigh these more heavily. And as a result, we come up with this context-informed
yeah.
network inference.
So I guess that there's one missing piece of the puzzle here, and that's that how do you know how well the forecasters and the influencers have done?
Right.
So I guess knowing there has to be some kind of element of ground truth in here, so that you
Yeah,
can get an actual loss. So the
exactly.
next participant, yeah,
Yes, indeed. So there is a third class of participants within the network, which we call reputers. And these reputers, what they do is they basically collect all of those different inferences. Because what you've noticed by now is that there's a long list of
yeah,
inferences, secondary inferences, all kinds of inferences. And basically, what the task is of the reputers is to keep an eye out of, okay, that's an inference for something that's going to happen at that moment in time. And at that moment in time, the reputer is typically like a domain expert in that sense, is that they can reliably source a ground truth for
yeah,
whatever is being predicted, and then compare whatever each of these inferences in this long list, compare that to the ground truth. And what that means in practice is these reputers evaluate the loss function.
yeah, and
And
yeah,
and those losses are reported back to the network, and then the network can use these losses to set all of these weights, and or well, to accumulate this historical reputation, because there is like an exponential moving average, so a form of historical smoothing on all of this historical performance, on these losses, and it is basically smoothing over these to generate this historical performance, set weights, and basically that is a looping cycle that just continues all the time, and that is how the network stays up to date and improves its inferences.
Right, and I guess this smoothing is important because there's going to be some level of randomness or stochasticity, and what you really want is, everyone has a bad hair day once in a while, and you don't want, just because someone's been great predictions and then they just have one time where they're off and then they're back on their game. You don't want to sort of throw them out. So there's, I guess,
That's right.
trying to find a balance there. It's important.
Exactly. That's actually, yeah, is maybe a little bit of a point on the side, but we have actually done quite careful optimization of parameters related to that, because indeed you want to, yeah, on the one hand, reward consistency, or not even reward, right? Because we're not even talking about incentives here. We're just talking about how you weigh inferences in your network inference. So you want to make your weight adjust
Yeah.
to a certain degree of consistency.
Yes.
But also, if there is a notable change in performance, you want to respond to that quickly. So that's an optimization game, but we've found a reasonable optimum.
Okay. So I guess following on from that, so how does self improvement work in this sort of decentralized intelligent network?
That is something that I think is central to any form of machine intelligence network, because basically you end up in this situation in practice where the problem you're trying to solve, so the inference you're trying to make, is continuously changing. So you constantly need to adapt to everything that is happening, and that is what these models, of course, do naturally, right? So the models naturally update their training data, retrain, and so on. They take the current context to make their predictions, generate their inferences. So there's this sort of constant adjustment to what the context is, right? So it's basically also propagating through this context awareness of the forecasters that we were
Yeah.
talking
So
about
the
before.
instead of being good on a Monday, they become good on a Tuesday, for example. So they
Right.
have to learn after a couple of weeks. Actually, Monday's bad and Tuesday's good. So
Exactly. And then what the forecasters do is, because they're just learning, they'll pick up, oh, wait, my timestamp is actually after this moment in time right now. Therefore, it turns out inference worker 2, model 2 is now good on Tuesdays.
yeah,
And on Monday, I should actually be listening to the first one. So that is something that these models adjust to, especially if you retrain regularly. So in that sense, it's sort of an intrinsic property of machine intelligence to always self improve. But there is an additional aspect here, which is basically what we were just discussing, right? In this sort of smoothed reputation,
yeah,
where we're constantly updating the reputation based on what the latest performance was. And if the latest performance was bad, then we're constantly like decreasing the weight a
yeah,
little bit. So there is a sort of continuous reinforcement of highly performing models, right?
yeah,
Where the weight gets boosted because of high performance. The incentives or the rewards paid out to different participants are of course are also dynamic, depend on their performance. So the entire both the rule set and the incentive structure are basically chosen uh, to reward self-improvement and to foster self-improvement. I think that is probably the main thing, is the self-improvement really comes from the fact that the entire everybody in the network is constantly incentivized to do their best to adjust to the problem set, and the roles are such that the network itself too sources the most recent and the most relevant information always, because in the end, if any of the participants, so let's take a forecaster, because I think it's sort of an interestingly complex example to illustrate this. Let's say a forecaster doesn't pick up on this idea that now turns out model 2 is good on a Tuesday instead of on a
yeah,
Monday. So let's say it's a Tuesday, and let's say that forecaster therefore forecasts the losses wrongly.
yeah,
Then what will happen is that in the weights of the corresponding of the forecast implied inference for the forecaster, model one and model two will be flipped. So it's listening mostly to model one instead of to model two.
Yeah.
Model one is wrong, model two is right. So it turns out then the forecast implied inference is going to be poor.
Yeah.
So then by the time the grand truth is revealed, the reputers will see it and go like, well, that forecast
All
implied
forecasting. Yeah.
was very poor.
Yeah.
Much poorer actually. Like if we had excluded that from the network would have done better.
Right.
So
That's a good
therefore,
metric. Yeah.
yeah. So therefore, we are going to, yeah. I mean, it just reports the loss to the network. The network realizes, okay, well, how had we excluded that, we would have performed better, and therefore that forecaster is going to receive less rewards. So
Yeah. Yeah.
in the end is very sort of algorithmically aligned to do that.
Yeah, and conversely, if someone had spotted the change, so the first forecaster to spot the change to Tuesdays is going to, obviously, the
Yes,
network loss or the network's going to be performing. If you take that out, the network will do worse, and therefore, it's so there's a strong incentive to pick up on these trends as soon as possible.
exactly. I like the temporal aspect that you're highlighting there, right? Because it is the same in, let's say, financial markets. Is whoever spots something the earliest reaps the greatest
Reward.
benefits,
Yeah.
and the same is true here. Because if you're the only one to realize, hey, indeed, it turns out now on Tuesdays model two is better, then you are probably going to be the one who's raking up most rewards,
Yeah.
or at least out of the pool that goes to forecasters in that case. So
And I think, as in in any market conditions, as soon as the other forecasters go, "Oh, hang on," and they see that, then the market will self-adjust, and so you get that advantage first of all, and then they will probably learn quickly. But as a result, the overall network as a whole is learning and improving. So you get
exactly.
rewarded for that spotting it first, but then the overall network learns, and everyone wins.
And that is indeed, in a way, why an intelligence market is so efficient in also economically democratizing intelligence, right? What we mentioned in the beginning. There is now when you're in a setting like that, there is no incentive to withhold information. In
Because
fact, by
everyone wins.
sharing the information, you are better off economically as a
Yeah.
participant.
So I guess this is a good point to maybe bring. So we've gone through all that. What about the the big groups, the big models, and this kind of centralized AI systems? Can something like Allora compete with those in terms of real term adaptability?
That's a great question. I think in many ways, the efficiency and adaptability of decentralized machine intelligence networks in general, but Allora in particular because of its context awareness, I would say that the real-time adaptability of Allora is much much higher by definition because on the one hand there is if you look at a siloed form of machine intelligence or basically just a single model,
Yeah,
then you're exclusively relying on that single model to retrain frequently, to adjust to all of these sort of changing conditions and so on. In a decentralized solution, all you need is now not like the single basket that you've put all your eggs in to adjust, but you can rely on just one participant out of many to
yeah,
adjust. And then the network will pick up on that.
yeah.
So
And
basically, that's a form of incentive aligned sort of real time optimization that addresses that does that kind of by definition.
yeah, and I imagine in most circumstances that you could think about that the sort of decentralized, the smaller units are easier to train, easier to pick up on these things, and easier to propagate. Whereas if you've got one monolithic that will take goodness knows how long to run, that being adaptable to spot those changes. I mean, fair enough, you spot them, but then to implement it and retrain and get that working again, there's a sort of momentum or time lag here.
Yes. So I think that is true. There's also a high degree of um, um, Basically the architecture of a decentralized machine intelligence network is different, right? And that's what you're alluding to. But in Alora's specific case, what you see is that the network is actually composed of what we call topics. And
Yeah.
topics are basically sort of segments of the network where participants collaborate to solve a single well-defined problem. So um, let me try and give an example. Like basically, these models predict what the weather is going to be in San Francisco tomorrow or in 24 hours. Let's do that, right? Okay, that's what they are doing. Now you can imagine that that is a simpler task than trying to predict the weather everywhere in the world, for instance, or to predict the weather everywhere in the world in a year from now.
Yeah.
So there is basically a degree of specialization, and because you do that, the models become sort of easier to update, to let them adjust.
Yeah.
But most importantly, you can parallelize these efforts.
Yeah.
And because you parallelize them, you don't have to wait for a monolith to retrain, but
Yeah.
you can say like, okay, we should probably retrain that part, and there will be some participants in that within that topic who retrain, but then participants in another topic that maybe predicts the weather in New York in 24 hours uh, doesn't need retraining, has actually been doing pretty well. And because you're basically differentiating that, because you're distributing, you can be a lot more efficient in terms of indeed that time lag that you were alluding to. Um, and you basically end up adapting to changing circumstances again in a much more bespoke way. So it's not just the sort of the uh, inference synthesis mechanism or the incentives for the individual participants, but it's also just how this sort of machine intelligence network is structured more generally.
Yeah. And it will spot that it always rains on a Monday morning in San Francisco, earlier than the big mall, or maybe it just feels like that Monday morning blues. But
Yeah.
okay, so then what are the mechanisms that prevent these decentralized networks from, I guess, devolving into inefficient or adversarial coordination?
um, so if you I think one big part of it is to differentiate your incentive structure, right? I think we spoke about that a
Briefly,
little bit already.
yeah,
But to give you an example, I mentioned that there were these three different roles within the network of inference workers, forecasting workers, and reputers. The inference workers should be rewarded for the quality of their inferences.
yeah,
And there are actually two layers to that. One is I want to know how much worse the network inference or better the network inference would have been had I not considered their inference. And I also would want to know how much better or worse the network inference would have been had the forecasters not been able to consider that inference, right? So there is a direct effect of this single inference, but
yeah,
then also as the forecasters forecast losses, and then all of these inferences are combined and forecast implied inferences, you can imagine that maybe these forecast implied inferences. So let's take the example, right, where we said that model 2 was now good on a Tuesday. And let's say we now say, okay, how much worse would forecasters have been, would the forecast implied inferences have been had we removed model 2 altogether?
yeah,
And it's not just that you're removing model 2, but you're also making the forecast implied inferences worse because they're relying on model 2 quite heavily on that Tuesday.
yeah.
So there is this sort of direct and indirect through the
Yeah, it's
forecasters.
a propagation through.
Exactly. And you need to basically carefully calculate what the impact is of each individual inference on the network inference that way. And if you do that, then you can reward them properly. You can say, okay, an inference worker with a more positive impact on the network inference, which you can measure by taking it out, should be rewarded more than an inference worker that has a less positive or maybe even a negative impact on the network inference. And there is again a little bit of optimization there, because you can imagine that there is some quantitative metric through which you measure this, which is basically just how does the loss change.
Yeah,
But then how many units of loss change convert into how many units of reward difference.
Yes, absolutely. Yeah.
Right. So there is a slope there that you need to tune. And then similarly, actually, when we were talking about inference synthesis earlier, there was a similar type of mapping between historical reputation and weight. There too, you need to make that type of decision. So these are, some things we've been playing with to try and optimize and balance these incentives correctly. So what I said there only applies to the inference workers, but you can imagine you can ask the same question for the forecasting workers. If I now
Sure.
take away a forecasting worker,
Yeah.
let's say I take away the one forecasting worker that was the first one to notice that Model 2 changed its outperformance day from Monday
From
to
Monday
Tuesday.
to Tuesday. Yeah.
I take away that forecasting worker, and all of a sudden the network doesn't know
Yeah.
that Model 2 is now good on a Tuesday.
And
So
that'll be reflected in the combined loss, or the how the
exactly.
performance of the network. Yeah.
Yes. So therefore, then that forecaster should probably be rewarded more than
Rewarded.
the other
Yeah.
forecasters, right? So again, there is that sort of incentive structure that's oriented towards that context awareness of the forecasters. And then finally, for the reputers, I don't actually care about any of these things. I just care about the fact that they're speaking the truth. And
Right.
that actually that just brings us back to a very traditional sort of blockchain problem, which is the Oracle problem.
Absolutely. Yep.
Is how do you do that? So for reputers, there is actually a relatively straightforward solution to this, which is that they need to be rewarded uh, in proportion to their proximity to consensus.
Okay.
So
So is
what
this
you can
kind of a game theory sort of
exactly
idea? Yeah.
what you can do is you can combine the losses reported by reputers, which again is always a long list, right? Because there's a long list of inferences, so it's kind of it's a vector,
Yeah.
and you can calculate something that we call a consensus vector, which basically combines all of the loss vectors of all the reputers into a weighted average, and that weighted average is the consensus vector, and then for each reputer you basically calculate how far away the loss vector of that reputer is pointing from the consensus vector. So you want the rewards of the reputers to be inversely proportional to that. Basically, the closer it is to
Yeah.
the consensus vector, the more they should be rewarded. But of course, you also, because again, I mentioned this is just the traditional Oracle problem in blockchain, kind of, you want reputers to stake, right? So in Allora too, reputers are staking entities.
Yeah.
That's not necessary for the workers that I just mentioned, because again, they are just getting rewarded for positive contributions and not
Yeah.
rewarded for negative ones. But for reputers, you definitely do want them to stake, because the stake is kind of them putting their money where their mouth is.
Absolutely.
So in the end, what happens is you want to reward them in proportion to their stakes. You also want to reward them in proportion to their proximity to consensus, where both can have similar weights in principle, right? So you can compensate one a little bit with the other. But of course, if you're completely off, there is very little you can do. We also handle that sort of. We have a relatively smart way of handling that in calculating the consensus factor, because the question is, of course, is how do you set these weights? If I calculate a weighted average of everything the reputers provide, okay, what are these weights? And typically, it's not like the standard thing to do maybe is to just let the stake define that weight, right? Say if a reputer stakes a lot, they're putting their money where their mouth is, so maybe they should have a lot of weight in the consensus
Could
factor.
be dangerous though, I imagine, if you've got someone that's up to no good.
If you do that, you can buy the truth.
Absolutely.
Uh, so you can't do that
Yeah.
actually. What you have to do is you want to let stake play a role, but you want to taper it off and have diminishing returns,
Yeah.
so that basically it's not worth buying the truth. And the critical point for that transition, you don't want that to be an absolute point. You want that to be something like, what's the average stake across all reputers, and
Yeah.
basically have it
Related to
that.
network size, for example, like the number of.
Exactly. Yeah, indeed. And that's what an average does.
Yeah.
So if you do that, then there are diminishing returns at some point for the stake. And basically what matters is also this element of a majority vote. So there is a suitable balance between that. And then as a result, you're capable of defining this consensus in a relatively objective way.
Yeah.
so that independently of the amount of stake of a reputer, if it's far off from the consensus, its rewards will always be low. And the fact that it has a high stake will not be able to influence that consensus by a lot. Basically, because it got tapered in the end, it gets outshouted by the numerous other ones that
Yeah.
are
So
participating.
like a large number of truthful people will outweigh
Yeah,
nefarious actors, basically. Yeah. And the stake is a way of ensuring that everyone's got skin in the game
yeah.
to make that happen. Yeah.
Yeah, it's more like an entry ticket than a way of sort of wielding your power,
Yeah.
and I think that's the thing. It's like it's a way of getting in, but when you're in, you need to
Yeah.
to play nice.
But how does okay? So I mean, this is great. We've got a network and everyone's sort of fitted in. We've got our forecasters and
Mhm.
people doing inferences and our reputers that are doing the ground truth. So why doesn't everything just get stagnant? We say, yeah, this is great. We're doing pretty well, doing good overall network inferences. Let's sit back and have a cup of tea. Like what's to stop that happening?
Yeah, it's like a form of collective underperformance.
Yeah, I mean, you can I can absolutely imagine a scenario where that would happen.
So the nice thing is when that happens, all you need is one participant to say, "Well, if everybody's underperforming and I don't, I get all the rewards." So there is actually no incentive to do that. If you do that, you just drop off because in the
Right. So
end,
this is the spotting the Tuesday thing, and you
yeah,
clean up
yeah.
while everyone's napping. Yeah.
So as long as somebody recognizes that and acts on it, then you're typically good. Um, the, there are some subtleties with that though, because there is, as with any system, there is a maximum number of participants that the network actively listens to, so to say.
Yeah.
So there is something that we call an active set. And that is true in any solution. Is your participant set can't be unbounded for computational reasons. That is just not possible.
Yeah.
So, okay, the moment you say there is a maximum, then you end up in the immediate problem that you need to
Who?
somehow define what
Yeah.
this active set is. Like, who is going to participate?
Yeah.
Who are we going to listen to? And there are many different ways in which that is possible. Of course, again, you can do things based on stake, but that is not desirable because, especially for workers, in the end, I'm caring about how well they're doing much more than what their capital is.
Yeah.
So, what you can do is you can somehow select based on the performance of the participants,
Hmm.
on their score, or maybe again something like an EMA or an exponential moving average of their
Yeah.
score, right? So some degree of smoothing so that their bad hair days get overlooked.
Get
But
washed out.
exactly, but by and large, that is what you can do. This is a mechanism that's fairly analogous to what they called sortition in classical antiquity, where basically the democratic system worked such that people were randomly selected to participate in elections. And I think that worked as a concept, works well in a decentralized machine intelligence setting. But the problem is, of course, is that you don't want it to be random selection. You want it to
No.
be merit based.
Yes, absolutely.
So that is why we introduce something we call merit-based sortition, which is basically we take the historical scores of participants and basically at any given epoch or cycle
Yeah.
of the system, we basically select the ones who, with this smoothed score, are the top ones in the list. Now, if, because that was your original question, if suddenly the network collectively, or the participants in the network collectively start underperforming, then they're going to drop out of the active set because there is always somebody waiting in the
And
wings. And
hungry, trying to improve their models in the wings, wanting to get in for
that's
big
right.
selection.
They've not been underperforming. And then what happens is they get in,
Yeah.
and all of a sudden everybody's put to shame because there is this new participant who is actually doing their work well.
Yeah.
So that is, I would say, is very important. Is to have these fluid participation dynamics, where you kind of constantly have to prove yourself as a participant that you're worthy of being
You,
part of the active set.
that you're
And
contributing positively to the network
exactly,
performance.
and what that does too is you can imagine that there are maybe certain workers, be it inference workers or forecasting workers, doesn't really matter. But you can imagine that there are workers who maybe discover that introducing some new feature data actually has a really positive effect on their
Yeah.
accuracy. One like that can be waiting in the wings, and the moment, like over time, it'll get closer and closer to the active set. There was a constant sort of trend. There was an attractor at the boundary between the inactive and the active set. So
Yeah.
eventually, everybody will get promoted. And the moment somebody has discovered this new feature data and makes it into the active set, again, the whole network adjusts. So it's not possible really with this merit-based sortition infrastructure to get this sort of ossification of the
Yeah.
network. That's not possible.
Stagnation, yeah, ossification.
Yeah.
Yeah. Wow. So on that, I guess it's this idea of a sort of evolving, a time evolving networks. We've had some really interesting discussions about this in more broader context, and I'd be interested in what you're thinking about sort of how this relates to biological swarms and things beyond what we've been discussing already.
Well, I think it's very inspired by biological swarms and so on, because in many different ways. On the one hand, I think Alora's design is very much inspired by evolutionary biology. Um,
Survival of the
Basically,
fittest.
if you look at the evolution of intelligence, there is this constant process of adaptation where traits that increase fitness. So basically, in biology is the ability to procreate, but in machine intelligence is the ability to perform. Basically, traits that increase fitness are selected to become more prevalent.
Yeah.
And the same thing is true almost literally in what we've been discussing about decentralized machine intelligence here, right? Is if yeah, just going back 2 minutes to the example I gave of a model discovering that certain feature data help its accuracy,
Yeah.
well, then you're introducing this trait that increases fitness.
Yeah.
And as
Absolutely.
we discussed, it sort of it floats to the top of the food chain. And that same thing you see in evolutionary biology a lot. The other thing that is interesting is that in biological swarms, you have a form of safety in numbers, right? I as a kid, I found it absolutely fascinating that a bee can only sting you once and it will die.
Aye. Yeah.
That is to
That can't be a good option, surely. Like for the
right,
bee.
exactly.
Yeah.
And of course, indeed, as a species that cares a lot more about individuality, like us, that is a very alien concept. But if you're a species that actually relies on safety in numbers and relies on swarm dynamics for its survival, it basically becomes it's a very simple evolutionary mechanism. If there is a bee colony that one way or another, because of some mutation, decides that they don't want to sting anymore because then they die, well, then they'll get eaten and they won't be able to reproduce. So what you see there is that the longevity of the individual actually depends on the longevity of the swarm. So there is an incentive for the swarm really to say the individual doesn't matter as much. Now, the same thing happens when you create swarm intelligence or decentralized intelligence. Because if we just go back to the example of Allora, where you have these topics where there's parts of the network that solve a certain problem together, then of course these are together in a way are competing for rewards within that topic, but they're also collaborating because if they do poorly, then there will be fewer, like network wide, there will be less rewards flowing into that topic
Yeah.
and therefore they themselves will be getting less rewards too. So their individual fitness and longevity is actually tied directly to the success of the topic. That means too that participants in Allora who potentially are only active in maybe one or two or a small number of topics have a vested interest in that topic being successful.
Yeah.
So I also think that there is in some ways there is a potential evangelistic property to what the participants in Allora ought to be doing to make their participation successful. Is, let's say somebody is participating in a topic that does weather prediction, as we already said, right? And somebody else is participating maybe in price prediction in the stock market or the crypto market or whatever. Then you can see that in many ways these are orthogonal use cases, orthogonal applications. And it is in the interest of the participants to evangelize these forms of decentralized machine
Absolutely. Yeah.
intelligence outside of the immediate Allora community, but actually to spread their utility to just society at large and
Yeah.
say, like, look, if you use Allora or this topic here to inform your decision making, then you're suddenly in a situation where you can outcompete your competition just because
Yeah.
you're using our intelligence. As a result, when participants do that, these topics will get better funded. Those participants within the topic
Well,
will
then
get
earn.
more rewards.
Yeah.
And not just that, they'll also be, in a way, competing against the other topics, right? So this is again is maybe a little bit more on a meta level, but is this form of of inspiration from swarm biology or swarm interaction in biology, where you see that the similar incentives, where it's not necessarily about the individual but about the performance of the collective,
Fold.
can
Yeah.
actually be translated very, very directly.
Yeah. That's fascinating. So yeah, I guess to finish, one last thing, sort of thinking a bit longer term. Can you how do you think decentralized intelligence is going to shape sort of the general future of AI ecosystems?
Yeah, that's a very important question. It will cement its role, I think, in the not too distant future, as a fundamental part of AI ecosystems. Because indeed, on the one hand, it democratizes AI. It enables a form of emergent intelligence. Again, sort of linking back to this biological uh,
Absolutely.
analogy. It distributes decision making. It is more robust to noise in general too, because you have historical smoothing reputation systems and so on. So basically, there are several aspects where it is just fundamentally more performant,
Yeah.
while at the same time democratizing this access and participation in machine intelligence. Right. So that I think that open participation is going to be extremely important. It will also, because of the transparency, be able to inform policy making better, to potentially make progress on things like alignment. It will. I think that is also an interesting part. Is it will allow the development of an application layer on top of the
Above.
decentralized
Yeah.
ecosystem that is completely different from other ones, right? We're very much talking about sort of agents these days,
Yeah.
AI agents, and
Absolutely.
how they can make decisions. So you get basically algorithmic decision trees with a certain degree of autonomy, right? That's what agents
Yeah.
are. But they're awful at quantitative stuff. So if you now have a decentralized machine
Yeah.
intelligence
Well,
network
imagine
where
doing that.
different topics are
Ah,
providing quantitative intelligence, and you let these agents utilize that input,
wow.
then
Yeah.
all of a sudden they can make informed decisions instead of
Yeah.
just
Quantitative. Yeah.
randomly deciding to stick with their philosophy, whatever it may be. So I think that's really important. We call these topic meta structures in Allora. And when we came up with the idea of topic meta structures, which is just let's combine the outputs of lots and lots of topics to say something meaningful and useful, um, we initially hadn't actually thought about agents. But within, I think, 1 or 2 weeks, as the agent meta was slowly starting to take off, we realized that topic metastructures are agents,
Yeah.
and that what Allora has become is the intelligence layer for AI
Really
agents.
need. Yeah.
And that means that as we're sort of approaching this world where AI agents are starting to play a bigger and bigger role, Allora naturally is going to play a bigger and bigger role in feeding these agents and making sure that they have access to the inferences, the forecasts, the predictions that are actually needed for them to function.
Yeah.
So I think this democratization of machine intelligence, coupled with the economic accessibility, the fact that there is an intelligence market, that intelligence is commoditized, that these all these participants are basically together making machine intelligence more affordable,
Yeah.
is these are all major factors in cementing that role of decentralized intelligence in the future. And what that means really is that, if you look at AI at large, is that the evolution of AI doesn't have to be that sort of race or arms race that's controlled by a handful of industry
Yeah. The kind
giants.
of current narrative. Yeah.
Exactly. So with decentralized swarm intelligence, you see a shift from this siloed, maybe a little dystopian future, instead towards a future where intelligence is distributed, it's adaptive, it is more intelligent, it is open to everyone. And what is maybe the kind of key insight from all of that is that in such a world, the strength of a network isn't contained in any single node or participant, but everything is really about how these nodes work together, what that infrastructure looks like. And that is exactly the role that we've been, yeah, basically trying to sculpt out with Allora.
That's certainly a very uplifting and different vision. Well, I think that's been, I mean, it's been absolutely fascinating. It's at the end of the discussion on this art, as I see it, of decentralized swarm intelligence. But we've explored the challenges, the innovations, competitive potential of decentralized AI. And I particularly enjoyed the focus on Alora's approach to generating this context awareness and self improving intelligence. So, if you're interested in diving deeper, please check out our research at alora.network and stay tuned for the next episode of the Allora Research Fireside Chats.